Hey, I'm the tutor for your circuits class, and I'm recording a solution to a problem that I was told you're having trouble with. So let me share my screen here. All right. So I made a little walkthrough here that I'm just going to talk through. So this is the problem that I was told you needed a little help with. The first step is to find IG, this current the current source in the middle of the circuit. And then we're going to calculate the power dissipated in each of these resistors and find VG, the voltage drop across this current source, and show that the power delivered is equal to the power absorbed. So the total power, when you add up the entire circuit, is equal to 0 always. So we'll check that at the end. So first thing we want to do is simplify the circuit as best we can. And we have these resistors, the 9, the 11, and the 10, that are all in series. So we can add up resistors that are in series. And same with this 16 ohm and 4 ohm resistor, we can add these two together as well. So you can see the total resistance in this top wire here is 30 ohms, and the total resistance down here is 20 ohms. So we combine these resistors that are in series, and then we just want to, for the sake of solving the problem, just label all these unknown currents. So we had IA and IB labeled, and IB accounts for all the current going all the way through this top wire. And then we're going to have IC here on the right side from this ground node that I labeled all the way up to here. Some unknown current IE here, and some current ID right here. And I've filled in arrows pointing in some direction. I don't know if that's the right direction or the wrong direction, but that's okay. Once we solve the circuit, we'll see if we get a positive or a negative current, and we'll know that if we drew it in the right direction or not. So we labeled these unknown currents, and then I labeled a ground reference. And this is just picking some spot on the circuit and saying, okay, voltage is 0 here, and we'll use that as a reference to solve for voltages in other areas on the circuit. As you start solving more of these circuit problems, you'll find that there's always a most convenient place to put your ground node. But you can put it anywhere, and it's not going to change the solutions to your problem. So in this particular problem, I thought that the best spot for this ground node would be right here, centered at the bottom here, just below the circuit, the current source. So now that we've labeled some of these unknowns, we can fill in the parameters that were given to us. So, and these might be different on your mastering engineering homework. They usually switch up some of the values. So in the book, this voltage source is 100 volts, and IA was 4 amps, and IB was -2 amps. So hopefully, if you have different parameters, you'll be able to follow along this guide and figure out the solutions for your problem. So this first, let's look at IA. This is 4 amps. This is labeled down here, right? But it's all the current going from this down from this node down through this voltage source and through this 15 ohm resistor to ground. So we can evaluate using Ohm's law the voltage drop across this 15 ohm. And we know that voltage always drops across a resistor in the direction that current is flowing through it. So since this 4 amps is going left to right across this 15 ohm, we know that the voltage is dropping from positive to negative, going left to right. And it's just the current times the resistance, V equals IR. So 15 times 4, we get 60 volts dropped across this resistor. So we just go ahead and label that. And then IB, they give us as -2 amps. So you see I've drawn it a couple times here on the sides by these nodes. And I turned around the direction and I make it +2 amps because it's just easier to, when you're given a negative current, intuitively you should think, all right, it's not, instead of saying negative current, let's just call it positive current and turn the direction around so that it's easier to solve the problem. So we actually have +2 amps, going left to right across this 30 ohm resistor. So same thing, Ohm's law crosses 30 resistor. We know that we have going from positive to negative voltage, left to right, and V equals IR, so 2 times 30 ohms, we get 60 volts dropped across this resistor at the top. So we filled in our known currents and we solved for a couple voltages, and we want to look for some other parameter that we can solve for. So we want to look for some KVL loop with an unknown, or maybe a KCL loop with an unknown. In this case, we can solve for the voltage across this 20 ohm by looking at this whole outside loop. So you know that if you do a KVL loop, it means that if you start in one spot and make a loop around, the total voltage has to equal 0, right? Because you have to get back to the same voltage. We know that there's 0 volts at this ground node. So we're gonna, as we go around this loop, we know that, so if we start here at the ground and go left, we know that we're gonna add 60 volts as we go through this resistor. It goes from low to high here. So we go up 60, and then up through the voltage source here, go up another 100, up to 160. And then around the bend to add this, so we subtract this 60 volts across the 30 ohm, right? So we were at 160, and then once we get around to here, we've gone down 60 volts, so we're at 100. And now we want to get back to ground. There's only one component left, this 20 ohm resistor. So we know that if we finish this KVL loop, we have to get back to 0. And once we got around to here, we've got up to 100, and we need to get back down to 0. So we know that there has to be a 100-volt drop across this 20 ohm for KVL to work. So we can go ahead and just fill that right in. So we know that there's a 100-volt drop here across the 20 ohm. And we can use that now to solve for the current that goes across this across this 20 ohm resistor, right? So we know that V equals IR again. So you can see that it goes from high voltage. It goes from high voltage to low voltage here. So current has to be going down this direction. So it's not going the way that I had drawn it originally. It's going the opposite direction. And if V equals IR, so 100 equals 20 times I, just divide by the 20 and you get 5 amps. So draw that in. Now we have 5 amps going down this way, and 100 volts here. So now that we know that 5 amps is coming this way, we can fill in some of these current values too. We just use KCL to solve for the remaining currents. So if you look at these two nodes at the edges, let's look at this one first on the left. So there's 2 amps going up out of that node and 4 amps going down out of the node. And you know that total current entering a node has to equal total current leaving. So if we have now 6 amps leaving the node and we only have this one unknown wire entering in, this has to be 6 amps, right? Because otherwise there would be we need to account for the 6 amps somehow, right? If 2 amps goes out to the top and 4 amps goes out of the bottom, we need 6 amps to come in from the right. So that this ID has to be 6 amps. And then if we look over here on the right side, we have 2 amps entering from the top and 5 amps leaving from the bottom. So we need 3 more amps to enter. So we need the total current at this node to be 0. And total current entering has to equal total current leaving. So we need 3 amps to be coming in. So it's drawn the other direction from the way it's drawn now. So we flipped this arrow around, and we know that 3 amps is going left to right here, and 6 amps has to be going right to left here. And now we can look at IG. IG, so if we have 6 amps leaving this way and 3 amps leaving that way, we would normally, we'd say, okay, so 9 amps has to enter, right, from the bottom up. But they've drawn this current source for us, so that we know that they want us to define IG as a current source pointing in this direction, right? So it's not something we can turn around. We just have to define it as a parameter. So IG is negative 9 amps because we know in reality that 9 amps is going up through it, but as that current source is pointing down, we just flip the polarity, call it negative 9 amps going down, and now the equation is balanced. And if you write, this total current leaving has to equal 0, because if there's no current entering, right? So if you add up all these currents, 6 plus 3 plus negative 9 equals 0. So that's just the way to think about it here. So now we have everything defined. As far as these resistors, we have all the currents. We know what IG is. The second part of this problem was to look at the power dissipated in all of the resistors. All right, so the general form of the equation for power is P equals IV. In some instances, it's going to be useful to combine this equation with Ohm's law like I have here. So there's other ways to write this power equation. You can say P equals V squared over R, or P equals I squared R. So these are useful sometimes when you're trying to calculate the power on a resistor. Sometimes it's just quicker and easier to use these equations. And you always need to use sign convention when you're calculating these power equations. Now, resistors are always going to absorb power, right? Because they're never going to deliver any power to the circuit, because there's always a current, a voltage drop across a resistor. So you should always be getting positive values when you're calculating power across a resistor. And then on sources, you're going to either get positive values or negative values, and that's going to tell you if it's positive, then it's absorbing power, and if it's negative, then it's delivering power. So keep that in mind when you are writing out these power equations. So we can go resistor by resistor and calculate these power values. So at the top here, we have you can use P equals IV or I squared R or V squared over R. So there's 2 amps going over to this resistor at 60 volts. So 2 times 60 is 120 watts. You could also do I squared is 4 times 30. You get the same thing, 120. So you go through each of these resistors and you just calculate that power value. And then I did the same over here for the voltage source as well. And that's just same thing. P equals IV. So 4 times 100, you get 400 watts. So all of these powers that I've labeled here are absorbing power because they give it positive watts. So that means that this current source has to be delivering power, because when you add up all these powers, the total has to equal 0. Right? So, but that's the final step. Before we get there, we want to evaluate the voltage on VG. So that's easy because we've already labeled all these voltages, right? So we have this voltage labeled and this voltage labeled. So let's just do a little KVL loop here, starting from ground. So we go up 60 volts, then up 100 volts. So we're up to 160 volts. And then up another 30 volts, we're up to 190 volts here. And then VG, that's just this voltage drop across the current source, and we're back to 0. So this VG has to equal 190 volts, right? That's this loop that we just did, this KVL loop. And so, and we can just verify that on this loop too, because we do the same thing. We go up 100 volts, up 90 volts, or 190, same thing, and then back down. So VG equals 190 volts. Sometimes it's helpful to verify that stuff using other sides of the circuit, just as like a double check, So yeah, VG is 190 volts, and then the final step was to just figure out what the power delivered from this current source was and verify that it balances with the power absorbed in the rest of the circuit. So if you look at power delivered by this current source, P equals IV, so current's going down through here, and it's entering the positive terminal, so we just use the normal IV form of your equation. If we were entering the negative terminal, negative voltage terminal of a device, you use P equals negative IV. But in this case, current's traveling down through this component, and it's the positive terminals at the top. So P equals IV, and it's negative 9 amps times 190 volts. So you get negative 1,710 watts. And you can check this if you add up all these positive powers of all the 5 resistors in the voltage source, you'd get positive 1,710 watts. So you add it together, you get 0, and so that everything's balanced, and you take a double check that you've done this correctly. So that's the problem. I hope that helps you understand how to solve these. And the more of these that you do, the easier you'll get on like identifying the tricks of like solving these puzzles and filling in the gaps. I have tutoring hours on Tuesdays and Thursdays from 10 to noon, so feel free to stop by. I can walk through any of these problems with you. I'm happy to do it. So I hope this helped, and have a great day. Thanks.